Hi everyone, today Shubha and me will be presenting this paper on full duplex techniques for 5G networks. Spectral efficiency has been a traditional problem in conventional half-duplex systems due to the inability of such systems to fully exploit radio frequency resources. In contrast, full duplex systems are able to double the spectral efficiency via simultaneous transmission and reception of signals, thus doubling channel capacity. In literature, the pros and cons of full duplex systems over half-duplex systems have been studied. Full duplex systems have the advantage of increased throughput, increased diversity order, and lower outage probability, but this is at the cost of higher algorithmic complexity. Self-interference, or SI, is also a major downside to full duplex systems. SI is inherent in full duplex systems due to the power difference between outgoing transmitted signals and incoming received signals. Furthermore, SI must be mitigated in order for full duplex systems to have better capacity against half-duplex systems. MAC layer protocols must also be adapted for full duplex mode operations. This is because systems in full duplex mode may not necessarily outperform systems in half-duplex mode. Against such a backdrop, a survey of SI mitigation techniques is discussed in this paper. Full duplex mode selection and MAC layer protocols are also discussed. The authors also propose a full duplex decode and forward relay scheme for cognitive networks with an analysis of outage probability for multi-relay cooperative communications. The challenges of full duplex system implementation, advantages and disadvantages of full duplex techniques, and potential future research are also discussed. To take advantage of full duplex systems, SI must be measured, managed, or mitigated. Failure to do so can result in reduced channel capacity. The authors noted, however, that if residual SI is at least 3 dB lower than noise, then the resultant effect of SI on overall end-to-end throughput will be minimal. To achieve this goal, a combination of SI cancellation methods can be used. These methods have been classified into either passive or active cancellation by the authors. Passive SI cancellation entails exploiting path loss or power attenuation via directional SI suppression or antenna separation. In directional SI suppression, the direction of the antenna radiating lobes are placed such that there is minimal lobe intersection. In antenna separation, path loss is induced either by physically placing the antennas apart or by making use of terrain features such as mountains. This method, however, is constrained by the size of the full duplex device. Other works on passive self-interference cancellation have also been noted. Sang et al. Proposed an antenna selection SI mitigation method for MIMO full duplex systems. Specifically, a subset of transmitting antennas is selected for transmission to reduce overall SI. But having additional antenna for the sole purpose of SI mitigation is also not spatially efficient. Everett et al. Proposed a combination of antenna directional placement, radio frequency absorbing materials, and cross-polarization. However, the gains from the proposed techniques are progressively diminished in reflective environments. Passive SI mitigation can also increase the frequency selectivity of SI signals, thus increasing computational costs for subsequent SI mitigations. Active SI cancellation entails mitigating SI with analog, digital, or a combination of methods. In analog SI, a copy of the SI signal is removed in the receiver analog circuit before it affects the ADC. The authors also noted that time domain training-based methods can be used to estimate and cancel SI. In addition, the degree of freedom via spatial domain diversity can also be utilized for SI mitigation. Specifically, MIMO systems can partition antennas into transmit and receive sets or antenna sharing modes. In digital cancellation, residual SI is cancelled in the digital domain via digital signal processing techniques. The authors noted zigzag as one such digital SI cancellation technique. Other works on digital SI mitigation have also been seen. Baradia et al. Used prior knowledge of the baseband IQ samples at the receiver for digital SI cancellation. In fact, the authors used a combination of analog and digital techniques for SI mitigation. Raihunan et al. Explored both MMSE and zero forcing for digital SI cancellation. Analog SI cancellation methods are able to effectively cancel SI, but such methods suffer from high algorithmic complexity as well as spatial costs due to additional circuits. Digital SI cancellation methods can eliminate residual SI and is independent of modulation schemes, but it can also address hidden terminal problems, but is dependent on the dynamic ADC range and it needs accurate knowledge of the discrete time models. Apart from SI mitigation at the physical layer, the authors have reported studies on full duplex MAC protocols to address end-to-end network delays and hidden terminal problems. Sahai et al. Was cited by the authors as one such example. Specifically, shared random backoff, snooping, and virtual contention resolution were proposed to maximize overall network throughput while maintaining user fairness. And now, Shubha will be presenting the rest of the paper.
Now we are going to discuss another issue with full duplex system. Theoretically, a full duplex system having infinite dynamic range and perfect channel estimation can perfectly eliminate SI signal. But there are few hardware limitations which a full duplex system has to face when realized practically, such as transmit-receive signal quantization, non-linearities, in-phase quadrature mismatch, and so on. All might erode the practical implementation of full duplex systems. Another practical limitation is at the receiver. Full duplex-based systems might not be capable of invoking some sophisticated combining schemes such as maximal ratio combining unless the source node and the full duplex-based relay are perfectly phase synchronized. In order to address this challenge, a co-phasing scheme can be employed in the direct and relay links, facilitating a significant coherent combining gain at the destination. Before leading to practical implementations problems of full duplex systems, we must first understand what is cooperative relaying. It has been identified as a promising solution for effectively combating the shadowing effects to extend the radio coverage and significantly improve the channel capacity simultaneously. Numerous relaying protocols such as amplify and forward, decode and forward, compress and forward can be employed for efficient relaying as a means of guarding against severe signal fading. Theoretically, the more relays the cooperative communication systems are equipped with, the higher degree of freedom provided by the relaying channels, hence promising improved performance quantified in terms of channel capacity and link reliability. Now we see how full duplex work in cooperative communication. This figure illustrates a simplest full duplex relay network consisting of one half full duplex source, one half duplex destination, and one full duplex cooperative relay node. Both the source and relay nodes use the same time frequency resource, and the relay node work in the full duplex mode with two antennas. Hence, spectral efficiency increases when the communication process goes this way. The source transmits signal to both full duplex relay and destination. At the same time, the full duplex relay forwards the signal received in the previous time slots to the destination. After understanding relaying, in full duplex communication, we have come to another limitation in practical full duplex systems realization. For this, it should be understood that full duplex mode may not necessarily always outperform half duplex mode in terms of throughput or channel outage probability, particularly when the full duplex devices suffer from high residual self-interference power. A hybrid scheme which facilitates switching between half duplex mode and full duplex mode may thus be expected to outperform either half duplex mode or full duplex mode alone. So there are few schemes for hybrid relaying. Time domain scheduling scheme was proposed for performing a hybrid relaying while formulating objective function as a nonlinear programming problem. Hybrid full and half duplex relaying is capable of achieving a superior performance in terms of its sum rate without sacrificing fairness among users compared to equal opportunity schemes. Second is opportunistic hybrid scheme. Opportunistic duplex mode resource allocation is motivated by resolving the fundamental trade-off between the achievable spectral efficiency and the attained self-interference suppression capability. Explicit conditions under which a specific duplex mode is preferred over the other can be provided, enabling opportunistic hybrid full duplex half duplex relaying to offer significant performance gain over this conventional system design that is confined to either of its constituent modes. As we know that the more relays the cooperative communication systems are equipped with, the higher degree of freedom provided by the relaying channels. Now we should understand how does full duplex relay selection works. In order to minimize the negative impact of self-interference signal on the performance of full duplex mode-based systems, an optimized signal-to-interference plus noise ratio of the source to the relay to destination link simultaneously, the relay having the lowest self-interference power among all the candidate relays can be activated. However, full duplex mode-based relay selection policies have not been widely explored, let alone evaluating their impact on the achievable system performance. Furthermore, the channel capacity of full duplex mode-based relay selection schemes may be significantly eroded by self-interference power. In this work, opportunistic full duplex relay selection scheme and underlay cognitive radio networks are studied, with decode and forward relaying mode being considered. The main contribution is full duplex relays instead of half duplex relaying in underlay cognitive networks, the impacts of the interference on the primary user and self-interference during relay selection process of decode and forward based underlay cognitive radio networks are analyzed. Now, the figure shows the performance of the full duplex relay selection scheme in terms of outage probability. Outage is plotted as a function of gamma SR, that is, source to relay SNR, for different decode and forward relays. We can see that when n is equal to 1, we get high outage probability, and when more number of relays, we have more degree of freedom, so outage probability have decreased. However, further increasing SNR may degrade the selectivity of the optimum relay due to serial interference being added to the primary user. More seriously, after the SNR approaching a certain level of 12.5 dB, further increasing SNR may cause all the relays to be dropped from the candidate pool. Now comes the remaining challenges of the full duplex system. Carrying out powerful self-interference cancellation increases both the cost and complexity of the full duplex-based devices, mainly because complex matrix computations have to be performed at the transceiver. Furthermore, the hardware limitations will also constrain the performance gain of the full duplex mode. Another challenge is low energy consumption issues. Since most wireless terminals are battery-driven and have limited energy harvesting capabilities, the energy dissipation of full duplex-based MAC layer protocols remains a challenging issue. It is of great importance to develop cost-efficient full duplex-based MAC layer protocols with low energy consumption in order to extend both devices' battery recharge time and the network's overall survivability. The full duplex mode philosophy was shown to outperform half duplex mode in terms of capacity gain, link robustness, and outage probability, provided the former operates at a low to high medium SNR values and information rates. Hence, expanding the benefits of full duplex mode to high SNR data rate regime is promising but challenging in practical environments. The feasibility of full duplex technologies in systems of wider bandwidth with high transmit power has to be further improved with the aid of improved self-interference cancellation capability, despite current techniques that can be effectively utilized in systems having relatively narrow bandwidth and low transmit power. Many critical issues such as problems of hidden terminals and multiple access collisions of distributed techniques, the requirement of low power consumption, and maintaining backward compatibility with existing MAC protocols cannot be readily addressed in the context of full duplex-based MAC layer protocols. Thus, an appropriate MAC layer protocol conceived for fully exploiting the full duplex mode benefits is definitely worthy of further study. Although a hybrid scheme facilitating dynamic switching between half duplex mode and full duplex mode is capable of outperforming either of its constituent modes, the hybrid mode based devices have to be capable of identifying the channel state information changes and promptly switching between these two modes. In the absence of centralized controller, a sophisticated distributed approach relying on self-organization principle could be employed by devices to implement cost-efficient hybrid protocol. Since a full duplex mode-based device has to process twice as many as packet as a half duplex mode-based device due to its essential capability of concurrently transmitting and receiving in single time frequency slots, both the PLR and the delay may become more severe for full duplex mode than for half duplex mode, unless a buffer skew length in the former is significantly increased. Nevertheless, striking the appropriate buffer size versus PLR delay trade-off constitutes a promising study item. These are the references. Thank you.